Can you test in the mic one more time?
Test, test. It still sounds like I'll just have to be.
Yeah.
I'll have to be. Test 1, 2. Okay. All right. Welcome to the Internet Engineering and Planning Group meeting. You probably have no idea who I am. My name is Joe Clark. I offered to present something in here, and Warren said, "Sounds great. Would you like to chair this?" Okay. Warren is at the IAB. Congratulations to him, I guess. And I will be your guest DJ for today, your delegate, Joe Clark. We have some great sessions and presentations to go over. So let's get right into what we're going to be seeing today. First of all, this is a very informal meeting, I'm told. We don't have the same kind of note well. We don't have the same kind of overarching governance, I guess. However, we will have an opportunity to bash the agenda. And what we're going to hear from is mainly some operational experiences and just lessons learned from operating, deploying certain types of networks. So it should be, like I said, a fun session. What we're going to do today is, first of all, you heard from me. Then we're going to hear from Jeff, Tobias, myself again, Mohit, and Andre. Each of these sessions is 20 minutes, which gives us, I believe, about 15 minutes spare at the end. So is there any agenda bashing? Anything else people want to discuss? Not seeing anything. Since we do have remote participation and obviously local participation, please get in on the Meet Echo tool. Even though this is an informal meeting, we still have Meet Echo. If you do have questions, please raise your hand either in the full tool or in the mobile version, and then you can come to the mic and ask your questions. Same thing online. I'll be looking for people who raise their hand. And we'll build a mic queue. What else do I need? We have a new slide bot. So you will, if you're presenting locally, you will have the ability to use the clicker to advance your own slides. And with that, Jeff, are you here? Oh, if you are on the full Meet Echo tool, please make sure your volume is off so we don't have cross noise. Right here.
Bring up slides.
I will.
Morning all, my name is Jeff Houston. This is not about the DNS or RPKI or routing. Yay. It's not about anything. Who knows about ECN? Okay, so you can go to sleep. There's a little bit to try and explain ECN because this is actually all about trying to measure the success of the efforts that have been going on for some years about L4S, trying to bring in low latency. And it's actually trying to change the way we signal from within the network the fact that some elements of the network are under load. So the current way TCP works is basically one extreme or the other. Keep on going faster until you load up the network buffers, until the network buffer overflows, until a packet gets dropped, or 2 or 3. Go until you drop packets. Once you get feedback that packets have been dropped, duplicate acts, you then back off completely and wait for that to actually drain the queue. Then you start again, preferably at about half the speed you were going before. So it's this classic sawtooth pattern, which you see in most, but not all, of TCP congestion control algorithms. There's friendly loss, there's unfriendly loss. TCP is bursty. If you lose a packet near the front or the middle of a burst train, the succeeding packets will generate duplicate acts. You will recover quickly. That's good. If you lose a packet at the end of a train, which is highly likely, then there's no succeeding packets to actually generate the duplicate acts. And you go into a long wait and retransmit timeouts, which is less okay. So the stuff that we use today is certainly, well, it's widely used, but it's not as elegant or as efficient as perhaps it could be. There have been various refinements to this that have tried to detect the difference between congestion and loss. And there's been a huge amount of work to actually understand how big a buffer size you should use in your network. If the buffers are way too big, then what will happen is you actually start to get standing queues, which means the standing queue is just the delay loop inside the network. You get higher latency, but not better performance. If the buffers are too small, what you actually get is overcorrection, and then you get idle points. The network has actually got spare capacity that you're not using it. So tuning the buffers in this kind of algorithm is actually critically important. And what actually happens, in fact, as folk who have looked at this and measured, tend to be that we get it wrong. And that's not surprising considering the huge diversity in both round trip times, congestion control behaviors, full round trip behavior times that are being imposed upon a common buffer inside the network. Now, what you're trying to do is to fill the network, but not the queue. And this was an observation that actually motivated the work on BBR, which tried to detect that point where you have filled the wire and you're at the onset of starting to fill the queues. You're starting to go slightly faster as a sending rate than you've actually got network capacity in the channel. And so the way this works is that effectively every 8th round trip time in the original version of BBR, you accelerated your sending rate dramatically. Shock therapy for the network. You increased the number of packets you send by 25%, which is a big increase. And you measure the round trip time across that interval. If it increases, then that means you're touching a queue. And that means that the speed that you were going previously to that inflation was actually not bad. If the round trip time remains the same after that shock therapy, press on and go faster because there's no queue that's being filled. So BBR tries to find that point just when you're getting at the formation of queuing behavior and optimize there. You notice in BBR, there is no need for a queue of any particular depth. You're not trying to fill it. You're actually trying to see when it starts. And so network buffer requirements for BBR are dramatically different from loss-based congestion. And so the way BBR works is that it's actually got its own low frequency feedback loop. It actually runs blind for 6 round trip times. It sets a rate and maintains that rate irrespective of loss events. It simply repairs them on the fly, still going at that rate. For one RTT, it lifts it up by 25%. For the next RTT, it drops it by 25%, such that if queues form, it gives it space to drain. So you notice compared to classic congestion control algorithms, which tend to oscillate around that kind of optimal point, biasing towards filling the queues, BBR is the other way. It's a pulsing behavior. But there's another way, and this dates back to 1990. There are a few people in the room in 1990. I see 2. 3, I was there too. 4, possibly 5. This is actually work done by Ramakrishnan. I think he was with Digital. And it's a ACM paper about actually enlisting the router to tell the upper level transport that it's forming congestion. It's an interesting idea of kind of cooperation between the infrastructure and transport. He was one of the ones I counted. I remember Rudiger as well, yes. And it actually came out in January 99, because things moved slowly in those days, as RFC 2481, an experimental RFC that effectively was trying to enlist the router to tell the transport that it's getting to the onset of queue formation, rather than waiting for the queues to fill, overflow, and everything to go bad. So that is January 99 with Ramakrishnan, who was then working at AT&T Research, as were others in the room, but not at the same time, Randy, right? You were there later. Yeah. And Sally Floyd, who pushed this through. I'm pressing forward. Oh, that's right. And a couple of years later, it changed from experimental to standards track. And David Black, I think, must have helped in getting it through to that point, much the same specification. So what happened since then? Nothing. It's actually a really neat idea. And it actually does manage to get early feedback on the onset of queuing without that weird view that BBR takes, because BBR does get it wrong as often as it gets it right, because it's trying to sort of remotely figure what's going on from the network with timing signals. And this is a much more explicit and definite piece of information that says, I'm having a problem, back off. So nothing. Until L4S, which is around 2022. Who's on this list of suspects? Bob Briscoe, he was very much involved. De Shepper from Nokia, Marcello Bagnolo, he doesn't come to IETFs anymore. And this was kind of adoption of ECN inside a bigger framework of trying to get lower latency with explicit signaling. It's a really neat idea. The way it works is you combine both IP and TCP. When you're pushing IP packets through a router and it's finding that it cannot enqueue it directly into the forwarding and send it off again, but it's actually going to sit in a queue, it simply marks the packet with a bit. Not all packets, it actually uses 2 bits. If one of those bits is already set, it will set the other bit. If neither bit was set, it'll do nothing, just forward it on. So if one bit is set, either one, it'll set the other and say, I'm having trouble. Now, it doesn't actually matter which router, because there is congestion on the path, says the fact that there are now 2 bits set. The receiver is expected to do something at the transport level to tell the sender to back off. And the way this works is that you bring in TCP, the reverse path. So you don't use ICMP because ICMP is a disaster. And you simply say in TCP, I had an incoming signal at the IP level to say queues were forming. Here is a TCP signal to say there is congestion going on, please do something. The sender then confirms that in TCP by setting the CWR flag and also backs off its congestion window as if there was packet loss. So it reacts before packet loss and tries to effectively respond to that congestion in a timely fashion without having to repair loss. So there are some bits, whoopee-doo. There are some more bits, whoopee-doo. So are we doing it? L4S has had a lot of push lately, particularly with Apple, going, this is actually not a bad idea. Let's go and do it. So at APNEC, Joao and I started to look for this inside the ad-based experiment we're doing. So over a few days, we picked up 303 million discrete IP sources from all around the planet and looked for the percentage of sources where we receive an IP packet that says, I can do this. One of those 2 bits was set. And interestingly, the signal is not crickets. It's actually not bad. 2.45% of sources are actually setting, the ECT bit. And fascinatingly, well, I find it fascinating because in general, the way this ad works, it pushes data out. It doesn't actually get the client to send a huge amount of data. But we did get 1 million with the IPCE bit, kind of going, I experienced congestion. Some router set both bits on the way through. So there's certainly a signal out there, and it's not negligible. On the IP side, there's 2 parts to this. In the initial SYN exchange, you set the ECN option flag to say, we're talking ECN. If that's not set, forget it. So around 2.5% of sources, much the same as the number with IP ECT, are actually doing the TCP option exchange. Of that, received end-to-end congestion experience, 0.27%, which is kind of feels right. There isn't much on the incoming. Congestion, CWR, congestion window reduced, a lot higher. Where sending, so congestion happened, it's kind of going, so I've got the signal, I have reduced my window. Pretty map, which is just what I've been working on the last few days. Hard to see, and maybe it's easier in Meet Echo, but the countries that are kind of doing something include the Indian subcontinent, cool, France, Germany, England, not so much America. From the signal we see in Russia, and it's not a big signal because ads don't really reach there in any great density, certainly see Russia, and bizarrely, New Zealand, yay. No idea why. The more the color goes to yellow and then green, and there is a greenish in Japan, the more there is IPECT going on. The closer it is to a rich red, Africa, there is nothing, not even at 1%. So the way this color kind of works is that the bias I can see that's deploying it is in Europe. Now it is slight, only a couple of percent, and across bits of Asia. Perhaps it's more recently deployed equipment, I don't know. And the other one, the TCP ones, where there is a handshake. I'm not saying whether there's congestion or not, but just, did you say that you can do the ECN dance? Now again, these are tiny numbers, up to 9%. And what I'm looking for is yellow and then green say there are more folk who are actually saying, we can do this. And here, oddly enough, there's a stronger signal coming out from America and actually a big signal from Vietnam. Again, Africa, nothing. Across Middle East, very little. What does it mean? It's really early days. These are tiny, tiny, tiny numbers. It's like looking for V6 packets in 1998. You'll find a couple, but not an awful lot. But it does indicate that there is an awareness about ECN and there is basically some degree of momentum for adoption. Here's the country table. Japan, France, New Zealand, India, Vietnam, and then Germany at the bottom are the sort of the countries where this signal is most evident, and the columns are both IP and TCP. So yes, on UK. So yes, it is gradually being taken up. What does it offer? It actually offers a better method of handling congestion than other forms of loss-based congestion control. It is a more accurate measurement that explicitly can react to the fact that routers are forming queues and actually allows the end-to-end algorithm to back off without necessarily going into packet recovery. And that's probably a good thing. And that's all I have. Questions?
You have 2, Randy and then Eric.
Randy Bush, Arcus. Notable TCP in the States, not IP. Any feeling of, is it hardware? Is it the protocols that are used, the applications that are used, the popularity of iPhones? Any clue?
I think the strong push is in the Apple ecosystem. But interestingly, if this was just Apple, I'd see higher numbers because iPhone's market share in many markets is around 10 to 16%. This is not that. And it's kind of, I'm not sure what I'm seeing. There is a definite signal. It's not just random bits in random packets. It's above that level. But beyond that, I'm at a loss to actually understand why at this point. Obviously, this is work that we're doing now, yesterday, today, whatever. And with luck, it might become a bit clearer over time. Thank you.
Eric.
Yeah, Eric Ving, Cisco. Basically the same question as Randy, because I think that's an OS thing, right? Even TCP is done into the operating systems. So, and I don't understand, for instance, from Germany and France, for me, they should be the same, right? The same amount of Apple device compared to Android device.
Spoken like a true Belgian, if I've got you right.
Yeah, exactly. That's the reason why thank you.
Thanks.
But it would be nice to get per operating system.
Look,
I don't know how to do it.
there's a bunch more digging that I think needs to be done to isolate who is doing these early steps, and equally a bunch of digging at the IP level to say where in the paths is the infrastructure actually recording congestion experienced. At the moment, all I'm doing is doing the endpoints. The endpoints are saying at IP, I can, and in TCP, I can. We do get a congestion signal, but the where's and how's requires more work. But as a teaser, this is not zero, and it's not crickets. There's kind of a non-trivial deployment out there.
Yeah. But are you using the flash, the good old, when you ask the browser to contact you back? Is it how it's done? The measurement.
Oh, I'm still doing this up there at the level of the ad and the browser.
Okay, but then you get the user agent string, right? Where you can get the operating systems.
Yes, there's a whole bunch more clues, and it's all a case of doing the archaeology and the captured packets. Yes.
Okay, thank you.
Thank you.
Jim, and then Alexander.
Thanks, Jim Fenton. I think this may be a very naive question, but I'll ask it anyway. How do these mechanisms behave in the presence of other sources of loss? I mean, with mobile networks and things like that, there's an awful lot more reasons why packets are lost besides just congestion. Do any of these have any negative effects there?
An ECN signal is meant to prompt in the receiver of that signal, backing down the size of the congestion windows and the sending windows as if loss had occurred. If loss occurs, it's the same reaction. Basically, loss by most of these algorithms is interpreted as a bit of a problem. Now, when I say most, there is some exceptions to this, because in the radio world in particular, where you get isolated packet loss, you don't wish to interpret that as a let's shut everything down and go slower. So you tend to get selective acknowledgement windows, SAC windows, and when you're using those and you get single packet loss, the answer is repair it and move on. This is simply radio noise. I'm not actually doing anything bad. As an experiment, Joao actually set up our outgoing system experimentally to set the CE bit for every packet sent. Communication came to a blinding, it wasn't a halt, but it was incredibly slow. So to some extent, there are a lot of folk, particularly in the Apple ecosystem, that are listening for this and reacting as if there was loss. Are we willing to unleash that on the rest of the world in a measurement? We're thinking about it. It does make things go a whole lot slower. Maybe that's a good thing.
Thank you.
Thank you.
Alexander.
Good morning, Jeff. I have two comments. First of all, so I'm a bit, I support adoption of ECN in a controlled environment, for example, in DC infrastructure. But if we are speaking about adoption of ECN in a wild internet, things become tricky, yes, because there are at least two issues that I see. First one is we are living in MPLS networks. And unfortunately, in MPLS, there is no place for ECN. So it doesn't break anything, but it just doesn't work because there will be just filling degrees and packet loss, no ECN. And the second comment is that, and it is, I think it's even more important that ECN capable traffic and non-capable traffic by default is not friendly to each other. It requires specific configuration on most devices, different profiles for ECN and non-ECN capable traffic. And if it is not done, the question is who will be starving. The other one will be winning, and it happens.
Don't forget, I'm not saying ECN is cool or advocating it, I'm measuring it. And that's a very different thing. I think some working groups actually working on ECN, isn't there? I think someone else in the IETF is doing L4S work. That's a great place to have the debate. Congestion RG is a good place.
Yeah. I'm not arguing. I'm just kind of surprised that a lot of people are enabling ECN in the wild, I think without knowing the consequences.
The Apple folk are very, very keen on L4S, and I think Ericsson and a few others have also taken up the charge.
Jen.
Hi, Jeff. I just like to clarify questions. So those like 7% I'm seeing on this slide is number of endpoints which support this, right?
IP sources.
Yeah, IP sources. So but I'm curious, it's another example of an interesting protocol which requires actually operators to do something for this to be useful and deployed, right? And did I read your slide right that you've seen about 16% of networks actually doing something with that, right? No?
I think that's pushing it a bit. It's still low, and don't forget these numbers are pretty small. So
So I'm just
early
wondering,
days.
like, we've seen that, right? What's happened when you can enable something on the client, but it's not used until the whole like underlying network infrastructure does this as well, right?
Yes, this at the moment is another presentation at some point if folks are still interested. This is the endpoint saying, we're cool, we can do this IP TCP loop and it will work. There is a second thing to go, how often is the IP I'm capable turn into IP a queue is forming, CE, and how often does that translate into a full back off of the windows in TCP? That's not in this data. It is in my data, but I don't send video files. I don't send anything big.
Mm-hmm.
Either the tiny packet interactions I'm doing encounter congestion, in which case they're kind of like random accidents on the superhighway that they just get marked because they were there at the time. And I can certainly get at some point the rates of that happening. It's not very high. I did say in one slide here, oh, that one there, 0.2% of TCP sources actually had a received congestion experience. So it's pretty small.
Okay, so basically you're saying about 2% of the routers on the way do something.
I think you're stretching the truth.
Okay, okay, I got it, yeah.
I don't have enough data to answer that.
Thanks,
And
Jeff.
with that,
Thank you.
thank you.
I think it's Tobias now.
So, welcome everyone. My favorite topic, DNSSEC, MTU, IPv6, and potentially some packet drops. Right, so what is this about? Parse MTU discovery, we all know and love it, but it's a mess. DNS is a camel if we can follow some person called Peter, which kind of includes most of the people doing DNS. DNSSEC makes it an even bigger camel. Parse MTUD for DNS given MTU breaks is kind of messy. And we do have this RFC 3901, which kind of leaves IPv6 for the DNS as kind of optional. So, quick recap, parse MTUD, IPv4, IPv6. Parse MTUD tends to break. So we have bogon sources, right, sending from RFC 1918, sending from IX networks, which is pretty fun if somebody is doing reverse parse filtering like Hetzner, which then leads to MTU black holes. ICMP might be dropped altogether, and, well, many other things, many other nice ways to break this. IPv4, well, MTU discovery is kind of meh, but in the end, on-parse nodes can always fragment packets, which should make things a bit better. In IPv6, only end hosts can fragment, and there is a bit of rumors that a certain tier 1 ISP is kind of a little bit dropping v6 fragments on transit, which I personally kind of think is not that nice touching transit traffic. For DNS and MTU, we have the issue that the times of 512 byte maximum DNS packets are long gone. DNSSEC makes packets even bigger. Not everyone is really into RFC 9715, which is for frag avoidance, saying eDNS zero size should be 1232. DNS over TCP makes things also not really fun. So we have a claim that IPv6 breaks DNS. And that is actually a discussion which has been going on for quite some time. I found this really, really nice article from Enno from 2015, which is close to a decade ago now, basically having the same discussion there. So, well, seems to be a topic. What we can do is we can make authoritative site measurements. What we can do, we like have authoritative service. We make a lot of clients resolve names on these servers, and based on whether they are able to actually retrieve a resource we point them to, we can figure out if they are resilient against certain alterations we might make to those packets. So for example, we might always want to reply with fragments, and if they can then actually retrieve that resource means they actually got those fragmented packets. Now, what we can also do is do it on the other side. So we kind of can check every single authoritative server out there, how they are dealing with clients being behind kind of not so favorable MTU breaking, parse MTU breaking networks. And the problem there is that each parameter we are adding, whether we are trying it with eDNS 512, EDS 1232, EDS 4096, each time we basically have to do requests for all authoritatives again, which kind of is a lot. And we actually do need a couple of those parameters. So we want to, like, if we would want to do this, we would want to do this for an MTU of 1500. We want to put like 1280 on the link of the host with which we are doing this. So when the host is then falling back to TCP, it can actually set the correct MSS. We want to do that with 1280 on parse. So the host doesn't even know what the correct MSS is for TCP fallback. We want to do this with parse MTU discovery working and not working. We want to do DNS resolution with v4 only, v6 only, and dual stack. And of course, we want to test a couple of eDNS sizes like 512, 1232, and 4K. What we can also do is, if we do these experiments, we can form hypotheses. So I don't really look like it, but in my day job, I'm actually something called a scientist, apparently. Also don't know how that happened, but it did. And we try to make these funny testable predictions, right? And if we have a prediction here, like, well, statement, DNS resolution is negatively impacted by IPv6 under MTU breaks, and DNSSEC makes things even worse, we can make predictions of how our measurements should actually look, or the results of those. Could say, for example, the no error percentage should be notably higher on IPv4 versus IPv6 only resolution, obviously because IPv4 is less impacted. The inverse for surf fail and timeout. There should also be more TCP fallback and too big packets for v6, as parse MTU discovery is more broken there. There should be more eDNS zero fallback, so this is a mechanic in the recursor I use, unbound. So if it doesn't really get UDP through with eDNS 4096, it after some tries will fall back to 1232, and there should be more of that. For v6, as parse MTU discovery there is more broken. Forced MTU breaks should notably impact v6 more than v4 in general, and those effects should all be more pronounced for DNSSEC enabled zones. What we can then do is we get a large list of name servers, or rather first we get zones. And for that, we took the Google Crux top 10 million. And for those, we identified like all the DNS sets that were being used, because technically we only have to ask each DNS set once. So we did that. We picked domains in a way that we would cover all DNS sets, which we discovered. And we also made sure that if there was at least one DNSSEC enabled domain on a name server set, we also picked those. And we've been running that once every day for a better part of 1.5 months now. This is all kind of open data, so you get like the ZDNS resolution logs, the ZDNS resolution results. You get PCAPs, which are a bit truncated because, well, otherwise my OpenBSD is not that good at capturing all those packets. You get the PCAPs of the intentionally dropped packet-to-big messages, all intermediate evaluation steps, all pre-generated plots, and all of that under data.measurement.network in the DNS-MTU-measurement folder. Out data. Currently, it's kind of still in a relatively rough shape, but I think this gives a nice first look. So let's look. You can make these really pretty comparison drafts, which are, I think, a little bit too small on these big screens. Might be better in Meet Echo. And what we see here on the left is the whole thing for zones without DNSSEC, and on the right for zones with DNSSEC. We do have this really nice color bar. If it goes more towards blue, it means like the ones on the bottom are smaller. And if it goes more towards red, the ones on the y-axis are smaller. And what we see here is that the biggest impact is in eDNS 5.12, because we have a lot of TCP fallbacks. And if we look at v4 versus v6, and of course we taken all those zones out that do not do v6, the difference is not that big. So we are talking about like 1% max. Funnily enough, for eDNS 5.12, TCP fallback seems to work a little bit better for v6 than for v4, for whatever reason. We can also do that for serve fail, and for serve fail, obviously on the side of not DNSSEC enabled domains, it's still dominated a lot by the issue that you sometimes have these zones that say like, hey, this is our v6 name server, and then there's nothing there. Right? That's why we have these red and blue bubbles there. Not that much on the DNSSEC side. So it seems like people doing DNSSEC might be a little bit better at either actually putting working v6 name servers out there or not doing it at all. If we look at timeouts, we kind of get a little bit of a gradient. It's again a lot worse for eDNS 5.12, of course, because we do more DNS, well, TCP fallback in DNS resolution. And again, the same pattern, we are kind of operating in the 1% range here when we come to differences between v4 and v6. Also something we do see when we look at like what packets we see. Obviously, there's a lot more TCP for DNSSEC enabled zones with eDNS 0 512, because it's a lot harder to get below 512 bytes. On like the no DNSSEC side for v4, that's not really there. But apart from that, they actually kind of do look somewhat similar for DNSSEC versus no DNSSEC. And especially if we look at DNSSEC enabled zones, v4 and v6 in terms of fallback kind of looks the same. Then we can look at packet too big. So how many too big packets did I see at the last MTU 1500 part of the network before whatever shenanigans I implemented thereafter came in? And we do have on the left packet too big, and on the right fragment too big. So if a fragmented packet ended up being too big, in terms of fragment too big, there's actually not that much difference for DNSSEC enabled zones between all cases. And the little dots, by the way, is like the total number of NSs in each of these categories. On the left, there's a little bit less packet too big for IPv6 for some reason. It's just kind of odd. And for zones without DNSSEC, there obviously is less in total of too big packets, of course, because we have smaller responses. And there actually IPv6 sees a bit more of those problematic packets. You can also look at the EDNS0 fallback for zones with DNSSEC, this time on the left for UDP fragmentation. It's a little bit similar to the previous packet too big issue. And also the zones without DNSSEC look pretty much similar to the packet too big thing. So it seems like when the packets are too big, in the end, we actually do get our fragments through. Interestingly, also for v6. UDP EDNS0 fallback, which I explained earlier, it's like when I try 4096, that's also the reason why for the others that is pretty much 0. And then unbound is like, well, it doesn't work, let's retry. That's a lot more pronounced for zones without DNSSEC and IPv6, which is a bit odd. And of course, it is occurring more and more the more you are moving towards broken networks. So the worst case is pass, well, 1280 on pass with broken pass MTU discovery. If we compare this between address families, we actually see that we do not see a lot. So this lightly shaded. So on the big screen, you probably don't even see it. Do I have a, oh, there. You don't even see it. Like on that screen, it's a bit visible that there's actually shades of colors there. The hatched parts are those where there's at least one of the two values missing in the comparison. But in the core of the things like IPv6 versus the others, there's really not that much difference in terms of number of fragments here between v4 and v6. For EDNS fallback, there is, as we see here, again in the roughly, which scale is that? It is the 100 scale, so somewhere between 1 and 0.5% difference, which v6 is worse, pretty much similar as we saw in the previous graph. But again, this is below 1% of all name servers. If we compare DNSSEC, again, similar picture. Of course, more fragmentation problems for our EDNS 4096 because we are just forcing bigger packets and hence more fragmentation. But that's basically about it. And what you might have noticed with this graph and the previous ones, the DNSSEC side always looks a bit more pale. So what can we conclude from this? Well, the first hypothesis thing we tested is that the no error percentage should be notably higher for v4 versus v6. And it's actually below 1%. I wouldn't call that notably. Same thing for serve fail and timeout. There's no notable effect. We are in the 1% range. We also had that there should be more TCP fallback and too big packets for v6 as pass MTU discovery is more broken there. Turns out TCP fallback is mostly an EDS 512 thing and comparable between v4 and v6, especially for NSX hosting DNSSEC enabled zones. For non-DNSSEC zones, TCP fallbacks are mostly an IPv6 thing. But I think there's also a big component of those unreachable zones then triggering actually a TCP request, right? If it's not replying by UDP, you just try TCP. And for some reason, there's less UDP packet too big for DNSSEC hosting NS than for v4. Than for non-DNSSEC. That was a typo. We also had that there should be notably more EDNS0 fallback to 1232 for v6. There is indeed around 0.05 to 0.1% more NS with an EDNS0 fallback for v6 versus v4. If those are hosting DNSSEC enabled zones, bit more pronounced for v6 for NS not hosting DNSSEC enabled zones, which again is a bit odd. Forced MTU breaks notably impacting v6 more than v4. It's mild, so it's 0.25% impact for individual metrics, and it's more pronounced for sets not hosting DNSSEC enabled zones. And effects are more pronounced for DNSSEC enabled zones, well, effects are less pronounced for DNSSEC-enabled zones. And the hypothesis there is that people who are actually running out DNSSEC are just much more likely to have picked up an RFC in the last decade or two and actually do something about fragmentation avoidance, and maybe actually thought about making sure that that v6 address they put in their glue records is globally reachable and replies to DNS queries, which also helps a lot with this data. So in overall conclusion, yeah, v6 and DNS seems to be not that bad. One thing I'm currently still working on is getting one v4, one v6 prefix of mine upstreamed exclusively via LGI, via an unknown tier 1, which might be dropping IPv6 fragments to see whether this data might look different when the same experiments are conducted there. And they will hopefully be added to that list of open data as well. So, thank you.
Jen.
Jen Linkova. Question. So you have v4, you have v6, you have dual stack. Have you tested cases when your client is v6 only and there is a NAT64 or CLAT or both on the way?
You mean doing DNS resolution with NAT64? I haven't tested it. It could just be added.
Because there are some interesting MTU complications when you start adding 20 bytes to the header.
So the issue basically is like keep pestering me ideally over the next weeks while I also have to set up the unknown tier 1 measurement. It's basically just replicating the same stuff once more and getting that data out of there.
Other questions for Tobias?
Awesome. See you all in DNS Hub.
Thank you. Well, this is odd. Switching gears a little bit, I will say to Tobias that yes, DNS does work with IPv6, and it does work with IPv6 mostly, as we will see here today. So again, my name is Joe Clark. A little bit about me, since I figure most people in this room may not know me. I've been with the IETF now since I think '89 in Berlin, and right after that I got roped into helping with the NOC. So I've been at Cisco just a little over half my life, 27 years now. I started in our TAC, in our Technical Assistance Center organization, where I was doing a lot of hands-on networking stuff. But over time, I kind of aged out of that, and I really do like this stuff. I like network operations. So every so often, I get a chance to play with this. Here at the IETF in helping with the Network Operations Center, and in our event, Cisco Live, our customer-facing event, these days specifically in Europe, where I get a chance to practice what I preach. And the reason I wanted to come here today and talk to all of you, because you might not care why you're hearing about our customer event, we decided to do something bold this year. And we deployed IPv6 mostly, essentially RFC 8925 by default for all attendees. And we said, you know what, we're going to make this work. And so I am here to tell you a little bit about that story and focus on some other operational issues at the IETF layer that we encountered in this network. So our agenda, really brief because I only have 20 minutes, introduction of our network, some lessons learned, general lessons learned, and then some things more focused on our v6 mostly deployment, and then finally some specific stats, since stats seem to be the way to go here, things we did actually measure. Sound good? Cool. First of all, on the introduction side, I am representing a team of about 60. So I actually do the data center part. Yes, we bring 2 whole data centers with us. I mean, Jen and Google probably wouldn't call them data centers, but they do serve our applications that we use to run the show. Things like DNS, DHCP, identity providers, all of our network management applications. We bring 2. If you've ever seen the movie Contact, why build 1 when you can build 2 for twice the cost? That's our motto. We want to keep everything very redundant. But since I do the data center, I also do the DHCP and the DNS. And so I collaborated with this team you see up here, our wired core team, one of which you may recognize, Andrew. He's done some V6 things in the past, including Happy Eyeballs. And we decided, you know what? Last year we saw a lot of option 108 in our network. And we said we could probably do V6 by default, V6 mostly by default. And we kind of convinced the powers that be to let us do this because it seems kind of crazy, right? Attendees come, we have press, analysts, customers, partners. Yeah, we have some nerds, but in general, we have people who just want a network to work. But we also said, you know what? We want to showcase what a modern network can look like. And we want to prove that we can make this stuff work. So we got together and we decided, how are we going to do this? We settled on what option 108 value we would use. We settled on things like RA timers and all of this, and came together and deployed this network. The network we deployed looks like this. Fairly complicated, well, not complicated, it's actually very simple. It's just one big OSPF Area 0 network. But some things to keep in mind, this network is, other than the 100 gig backbone, we optimize or we choose for routing as much as we can, and bridging or switching where we have to. So down here at our IDF layer, this is where we actually, the layer 2, layer 3 demarc stops. So we have about 40 VLANs. Each of those 40 VLANs or services are replicated across all of about 150 IDFs. Keep that in mind. We'll get back to that math in a minute. Everything else is routed all through the core, out to the data center, out to the edge, which in this case was handled by the Amsterdam RAI. If you're familiar with that event center, it's just a massive event complex. They have their own AS. They provide us with V6 and V4 public address space, /24 of V4, /48 of V6. So that's what we're doing here. And we're going to focus on the edge up at the top a little bit later, but this is generally the network that we deploy. And we try to keep it as simple as possible because, again, we have 5 days to make an impression with our customers. It's got to work, but at the same time, we want to offer a modern network experience. So what did we learn in doing this just in general at the IETF layer? Hint, we ran into some massive non-IETF layer, like layer 2 type stuff, but we're not going to focus on that here. We'll keep it layer 3-ish kind of things that the IETF is working on. First of all, we've been doing this for a few years, and one of the things we were always seeing at our IDF layer is every so often someone's going to unplug the last of the port in a given VLAN. And by default, when that happens, the switch virtual interface, the SVI, the routed interface for that VLAN goes down. There's no more ports in that VLAN, goes down. We lose a whole set of routes, and I monitor the routing table because during the event, the routing table should generally be pretty stable or in our intranet. So we would get a diff and that would get recorded. And the core guys said, you know what, we can optimize for this. We can turn auto state off on all our SVIs. That way they'll always be up. But go back to that 150 IDFs times about 40 services. Turns out that our switches doing routing only allocate so much TCAM to allow for about 6,000 or so routes. When all of those SVIs are up and we finally deployed about 150 of these IDFs, we started to see flatlines on our TCAM. We were no longer able to process any more routes and things got very bad for us. We're going to fix this, but to work around it, we simply removed some of the reserved VLANs that we just allocated just in case, just to bring that number down, and we kept watching it and we kept monitoring it. So even today, simple things like routing and simple things like hardware still tend to bite us. The other thing that was interesting, because now the IETF is doing green work, and I said I'm the data center guy. We got some new data center gear this year, including some very nice GPUs, because if you're not doing AI, you're just not doing anything, right? Our data center, so we keep this up for 5 days, but a little longer as we do the setup. Each one of these was taking 5 kilowatts constantly. And that's just for an event. That's just for our attendees. So it's something to note that when we actually start to layer on the AI into this, we saw that each one of these NVIDIA GPUs was taking on idle 35 watts of power constantly. Whenever we asked it to do inferencing, so I took one of my self-service chat bots, turned it into Gen AI this year. Whenever we asked it a question and had to do inferencing, that one GPU, that one cycle shot up to it itself taking about 350 watts. Imagine having to do this for, if we'd open this up to the attendees, if this was something that was just constantly happening. So when I see the green working group, I admire the effort, and I think it's very critical that we're doing it. But the value that people want out of these AI tools is going to drive that power consumption no matter what. So, and this is why you see articles about companies going after nuclear power, just trying to find different ways of generating power, because ultimately this is going to happen. And even we were seeing it, even on our little, because we have to do this. We have to demonstrate this to our customers. We're Cisco, we've got to, right? So this is something interesting. Power was, we had the power, but we weren't certainly doing it greenly in this environment. And this is just, again, for our event. So that was general lessons learned. Now on to the thing you're probably most interested in, IPv6 mostly on the event. So again, this is our edge. We do carrier grade NAT. We've done it for a few years now for NAT 4.4. Turns out Cisco, the ASR 1002, the routers we're using, they didn't like both carrier grade NAT 4.4 and 6.4 on the same boxes. We learned that rather late, the joys of event networking. So we brought in 2 additional routers to do just the NAT 6.4. Each one of these routers had a 10 gig uplink to the RAI. In peacetime, which fortunately the whole event was peacetime, all of the routing happens out of Core 1. Core 2 is not doing anything, and we fail over, and we did test it, so we did that, but we would fail over if anything went wrong over to Core 2. So this is kind of how the thing was laid out. We ultimately settled on a /26 of public v4 for both NAT 4.4 and 6.4, but we didn't start out that way, and I'll talk about that in a second. And then downstream from the routers was 40 gig into the venue. Our goal was 100% intranet IPv6 traffic. Ideally, everybody just starts, because we're doing, not only are we doing v6 mostly and CLAT for clients that support CLAT on the default SSID, but we're also doing DNS 6.4 on the default SSID. So even clients that didn't support CLAT should be getting a v6 record, assuming they have v6 turned on and all of that, and it should be internally all v6 traffic. That was our goal. We didn't quite get there, but the numbers were impressive. Impressive, given that not everyone at this show was a nerd, not everyone had geeky setups on their computer. So here's our address space. That's our public /24, and we were using the well-known prefix for NAT 6.4 internally. I think I have it on the next slide in terms of, for option 108, we decided on 900 seconds, 15 minutes for the clients to call back. We figure if there's a break glass event, 15 minutes seems like it's not going to overload our DHCP server, while at the same time, if something goes wrong, it's going to take at most 15 minutes for clients to get a v4 address. For those who may not know, real quick, the idea here is a client says, I can do this CLAT, I can do IPv6 mostly, it will ask for 108. If the DHCP server gives it 108, it will not act the DHCP. It will not take a v4 address. Apple clients allocate 192.0.20 as their v4 address, so things like ping 8888 just magically work on your client. And we had a lot of attendees come up to us in our public-facing knock and ask us questions like, how does he have the same IP address I have, and how does this work? That was kind of cool. People were into this in what we were doing here. And if the client does support v6 mostly, it will do the client level address translation to do into the well-known prefix that it got from Pref 6.4 on the v6 side, and magic happens, you get v6 internally, and then if it needed to be v4, like it was only a v4 service like GitHub, then it would get translated on our NAT 6.4 gateways on the edge. What you're seeing here in the pie chart are the number of clients. Now, I'll tell you how I measured this in a bit. MAC address randomization aside, the number of clients that supported v6 mostly or option 108 by default, and those that didn't. Obviously, the number that didn't is greater. Windows did not yet do it. I think there's a number of Linux instances that don't yet do it. But the numbers of clients that did support it, again, very interesting and very positive. In terms of issues that we ran into, I don't think it's on this slide. Issues that we ran into, we initially allocated a /27 for NAT64 and a /26 for 4.4. And we found that the NAT64 was so popular. People just did not get off the default SSID, even though we provided a legacy alternative. I'll show you the numbers in a second. We ran out of translations. So we had to decrease or increase the age out time, or decrease the age out time, make it more aggressive to age them out. And we moved from a /27 on NAT64 to a /26. The biggest issue we ran into, other than that, configuration, our VPN clients, the Cisco Secure AnyConnect or Secure Client, however you may know them, if you were doing a split tunnel VPN, the client got a v4 address over the tunnel, but the Mac OS was still doing CLAT. So it would do CLAT for tunneled v64 or v4 literals, and that would cause CLAT to take effect, and it would send the 64 IPv6 address over the tunnel, which didn't go anywhere. We feel that's a bug. We don't know exactly where we're looking at it with Apple, but we only saw it on our VPN clients, and we only saw it if it was split tunneled and not locking down the whole IP stack. But that was the only, and it was very easy to work around this. We just said in those cases, if you have to do that, join the legacy SSID. But in general, this just worked. And people many of them had no idea they were going out over v6. So some stats to round things out. First of all, this is the management stack. A lot of it's bespoke. We put this together because we know it works. The most interesting thing is Big Buck Bunny. If you've never seen that Creative Commons video, this is great for monitoring your multicast traffic. We always have this running. Big Buck Bunny over there. If that stops, we know that there's a problem with the multicast or maybe a problem with the network. We actually had daylight in our NOC. That's something that's kind of rare. But we put all this together and we can monitor all of this data that we want, because these slides come out of a session we do for the attendees. We're very transparent. At the end of the show, we tell them, this is what we did to build the network. These are the boneheaded things that we did that went wrong. And this is what you guys did on the network. From a wireless standpoint, we peaked at 15,000 simultaneous users. We only saw 7% at peak join the legacy SSID. Overwhelmingly, most people were experiencing v6 mostly. And like I said, didn't even know it. They were just experiencing and grooving on that IPv6. We had a lot of DNS volume, 926 million requests. Google was the most popular. In terms of v6, so we've been doing this for a while. We've always been waiting for the year that v6 takes v4. Last year, we were very close. At 44% of the traffic to the internet was v6. This year, 51.5% was v6. When I drill into those numbers, had the GitHubs and the Slacks and even our own corporate laptops that we hard-coded our v6 umbrella addresses instead of v4, we would have seen 70.2% of traffic to the internet would have been v6. That's pretty impressive. And internally, we peaked at about 72% of internal traffic was v6. So we didn't achieve our 100% goal, but we did quite well considering where we've been and considering the audience. So one of the things I mentioned, how I measured the clients that did and clients that didn't. These were the numbers total of unique clients. Again, MAC address randomization, kind of there's an asterisk here. Obviously, clients that didn't was large. I wrote a packet capture filter in PyWireshark that filtered all. Technically, the DHCP server I'm using, the log would have told me this, but the log messages were multi-line. It was just a pain to, it was easier just to sniff the traffic, look for the packets that had 108, count that as a client that had 108, that supported v6 mostly versus didn't. When I filter this just to the main SSID though, the ratio becomes a lot closer. It's still, we'd love to see more clients support it, and we think we will once we see Microsoft add support for it. But this ratio is much closer in terms of clients that do versus clients that don't. So we hope to really remove, again, get to that 100% of V6 traffic within our network. And finally, the big number, this is how much traffic we push to the internet, down and up, for 20,000 attendees over 5 days. So that's generally how the show runs. And this is what we did for V6 mostly. And no one in the queue. How did I do on time? I know I have a problem. Yeah. Jen.
Nicola, thank you very much. That's really exciting. So I'm glad to hear that you did not have so many complaints. I'm wondering if you actually measured the number of tickets or whatever, support complaints you got.
The only complaint we got, the only one, was on the VPN clients. And we did get a few of those because people didn't read their email, didn't read the chat. But that was the only issue. More people were curious. We got about 100 different questions about why do I have this 192.0 address to the NOC. But the only type of ticket was the VPN, and there was about maybe 50 people who asked different questions on that, different iterations of that question. But no one else had issues that came back to us, at least, to the NOC.
Cool. Then I would love if you could take a look at the draft we have at V6 Ops about how to do this, because it's not in the last call, but it's stable. And the reason is I would love to see how IETF NOC deploys this and see if it changes anything in the document. So maybe your Cisco life experience would be very useful to see if there are any changes or suggestions for the document itself.
Sure. And we have a IPv6, IETF IPv6 mostly SSID here that I encourage you to join. We plan to do this by default in Madrid as well. Yeah.
Marco Davids, SIDN. Thank you. Great presentation. Bold question. Considering the success, are you thinking about gradually making this the default in your own product so that if somebody installs a router or maybe an access point, that it has IPv6 mostly by default instead of the other way around?
That is a bold question. We hadn't considered that. We can ask. There's a lot of, as you might imagine, a lot of product teams we have to go through at Cisco to do that. But we hope by evangelizing this and advertising it, we can get more interest. Already, we have Eric from engineering, Eric Veng from engineering here. We've got the attention of a few of the distinguished engineers at Cisco. Whether or not that turns into anything we start doing by default, I think that's a big ship to turn, but it's certainly something we can consider. Thanks for the suggestion.
I just like to comment on this. The problem is V6 mostly is an architecture, right? You need a coordination between your DHCP, your NAT 6.4 and other things, right? So it's not like a bit you can flip on a single device unless that device performs everything, like, I don't know, your home CPU, right? So it's a bit more tricky than just...
It could be something more in our cloud like the Meraki type architectures that we start to see something like that.
Tommy Jensen. I'm curious if you had any insight into how much of the IPv4 traffic was to IPv4 only available destinations versus things that are dual stack available that may have been using IPv6 if happy eyeballs had always picked IPv6.
Yeah, we've stopped doing some of that for GDPR reasons, looking at the traffic. We used to be very aggressive, and we could track users down to the bathroom where they were and what they were doing. That is we want to do more of that and try to figure out. Anecdotally, we think it's the Slacks and the GitHubs, but we didn't have, we didn't do the detailed analysis this year of that. But that is something we want to do if we can next year.
Well, don't get me wrong. I'm a huge GDPR fan. Maybe an experiment where A queries for a name that has a quad A in the cache just don't get answered sometimes?
Okay, I could do that.
So Tobias Friedrich, Max Planck Institute for Informatics, adding on that default thing, maybe a first step would be to leave v4 off by default and, you know, make all the onboarding, provisioning stuff, etc. v6 only available. So if you plug it in, you are not told to get to like some RFC 1918 address, but maybe the link local, whatever. Nice thing.
This is the balance between wanting to make sure the attendees have a good experience and wanting to make sure we're doing the best we can from a modern network standpoint. I don't know if we're going to get a lot of support on that.
Okay, last thing, because it weirdly just popped in my brain, maybe something like FE80 just for like CPE provisioning from like the inside or something.
Sorry, I missed the...
Weird thought that just popped in my head for like CPEs, etc. Because there you always have to like figure out the IP address range in RFC 1918 to get to like the control interface and stuff. Maybe something like FE80. Well, usually it should actually just be FE80 for that thing because it's like a CPE, but maybe that would be something to think about.
Interestingly, our bootstrapping and a lot of our automation is still v4 centric. That is one thing we want to do better with, and Andrew wants to do better with. So we'll see where that goes. Anyway, I know I'm over time now. Thank you very much, and I'll go back to being your friendly neighborhood delegate. Sorry, howdy. Okay, you're fine. Yes, I'm good. Go for it.
All right. Okay, hello everyone. I'm Mohit. I'm working as a associate professor in the Department of Computer Science and Engineering at the National Institute of Technology, Karnataka. Surathkal, it's a small place in the southwest region of India, right across the Arabian Sea. And I'm going to talk about our experiences of migrating our NITK Surathkal campus network to IPv6. Mainly, I'm going to focus on some of the challenges and opportunities that we found while we were working on this. This is my first IEPG presentation, so thank you for having me. It's a great pleasure to be here. The first challenge that we got in this project was to find people who can help us migrate the network to IPv6 because we come from academia. I wrote a project proposal to APNIC, and this is a project that has been funded by APNIC. So the funding part was actually easy, but then once the fund came, getting people to help us with IPv6 in our neighborhood was pretty difficult to find because we wanted to have about 4 to 5 full-time engineers to work with us because we have a campus size of about 25,000 devices spread across 300 acres of campus. So we thought we should have dedicated engineers work with us, but when we rolled out the advertisements and waited for 2 months, we could just find one network engineer who could join us. The only other option left with me to continue this project forward was definitely not to give back the funding to APNIC, but to do something, and we decided to train our students and see if they could help us. And I'm pretty happy to report that last month we completed the migration of the entire campus. It took us about 18 months. But the best part about this whole thing is this whole campus migration was led by students. And a couple of my students also have been to V6 Ops, and they have presented this work in the past IETF. I'm kind of summarizing all the challenges that we have faced. So going forward, I'll put down some of the observations that we had, and we are also in the process of documenting it. Since we are very new to IPv6 and we were doing all these exercises, if you find something that we can improve upon, I'm here throughout the IETF week and would love to know and learn from all of you how we can improve. So I've listed some observations. The first observation category that I have listed is router advertisements. We found that when we were actually turning off the router advertisements, basically when we said, okay, we don't want to accept RA. So we went to sysctl interface and said, okay, put it off. We don't want to accept RA. We could still see that the RAs were accepted and the roots were actually getting installed in the kernel. So we had to actually debug as to why this is happening, because we have explicitly said that don't accept it. And we found that, okay, there was a different setting that was there in system D network. And we realized that it had accept RA on, even if you turn it off in CCTL, it doesn't work that way. So, and how did we find out? This issue was identified when our monitoring tool that we were using and the reverse proxy that was running in the host, it randomly stopped working. So when we started debugging, we realized that it was because of accepting all the router advertisements that we were facing this problem. And then we realized that the root cause was the fact that we had to go to NetPlan system D and then turn off this setting. And then actually it started working fine. But yes, it took quite some time for us to understand why this was happening. Second thing is we have more than 7,000 students in the campus, and they are all energetic and they want to try different things. So they also plug in their own devices into the network. And then we started seeing arrays from unknown sources coming into the network. So any particular system in the network, can run array daemon and then start broadcasting the arrays. So what happened with one of our device was that it accepted an array from a source where it shouldn't have accepted, and then it lost connectivity. And then we started getting complaint from a couple of students saying that my device isn't working. And we realized that this complaint was coming from a hostel where we had just recently turned on IPv6. So we could understand that there is something wrong, and we diagnosed it, and we found that, okay, there is an unknown array that is being accepted by the devices, and the device is actually trying to route its packet through the route that was advertised from that array, instead of what it should have done by routing through our routes, which were the valid routes. So for immediate purposes, we set up the ACLs, and that solved the problem, but that raised two questions for our team. The first question was, how did the device end up selecting the route that was actually coming from a different array? And then after using BPF trace, we added, and based on the packet hashes, we understood that the kernel, the kernel decides any path that has an equal multiple routes, it will just pick up the one that it sees. And the second question that we had is, why did system D not realize that this path is not working and fail over to another path? When we diagnosed it, we saw that what actually happens in the kernel pulls only till the next hop. And if it's reachable till the next hop, then it assumes that the path is working fine. But actually the path was broken beyond that path. So we had this problem faced over there. Moving forward, second observation category that I have listed is we found there was a lack of dual stack support in many places. First of all was our captive portal. Although captive portals are not used these days in many places, but our institute was using it for network authentication purposes, and it was a built-in utility provided by our firewall, and it was on for several years. But the moment we started working with IPv6, we realized that our firewall provider, and hence the network authentication mechanism in it that was using the captive portal, it didn't work with v6. So it either worked with v4 or with v6, but not both. So for example, if I hit a website which is on v6 first, it will authenticate me with v6 and say, okay, I know who you are. But then when I go to another website, for example, say Stack Overflow or GitHub, or I go to overleaf.com, they don't support v6. So I need to fall back to v4, and then my captive portal would pop up again and say, you need to authenticate again. So it was irritating a lot of users because they had to keep on logging in again and again to captive portal. So what we decided is we reached out to the vendor, and the vendor said that they would enable the support for it, but we didn't want to wait until the next firmware comes. So we disabled the captive portal for now in the campus, and instead we have deployed EduRoam, at least for the Wi-Fi users. So we have 801x authentication for now, but we haven't done that much on the wired part. Another problem we faced was with our deployment. We have Kubernetes in the campus because students upload assignments on Moodle, and then sometimes they upload assignments in bulk. So we wanted some solution that can auto scale, and we deployed Kubernetes. Unfortunately, we were using an older version of Kubernetes that didn't fully support IPv6. We had a version which was less than 1.21, and it broke the entire setup the moment we switched on IPv6, because the Kubernetes cluster, the Kubernetes stack picked up the IPv6 address when we turned on v6, and then it internally enabled IPv6 for all its hosts, and then everything broke. We had to actually do a lot of recovery manually and spend a lot of time. And finally, we learned the lesson, and it's better to upgrade Kubernetes to the new version that supports IPv6. Another issue that we found related to the address assignment. Although this is not a best practice that you tag all your VLANs, but what we had done for experimental purposes in our test bed. So we set up a small test bed before we actually went on to do something on the network. in the campus, we saw something related to DHCP v6 on all the tagged VLANs. Our clients started listening to all the tagged VLAN and started obtaining multiple addresses per interface. And this was confirmed by us by seeing that this was happening on both the machines, Windows machines as well as Linux-based machine. When we looked into the community, we found that Windows actually doesn't treat this as a bug. It just says that it's a feature because primarily this is used by them for their SMB file sharing features. But we did find in the community, Linux community, mentioning that this is indeed a bug. And they also reported that they fixed it in the kernel version 5.15. But to our surprise, we were actually using kernel version 6 and more, but we still found this bug happening. So we need to still do little more effort. We need to put more effort to understand why this is happening. For now, we have just untagged all the VLANs, and that's not in the campus I'm saying, but it's mainly in the testbed that we had set up. We also found that the privacy extensions, which were actually enabled by some of the clients, were hindering our progress in terms of deploying IPv6. Maybe once the entire deployment is done, we don't care much about it, but while the deployment is happening, it's important for us to understand how we are doing in the deployment wise and whether we are doing in the right direction or not. So we were actually bothered a bit with the kind of privacy extensions that were there. It made it very difficult for us to analyze our traffic at the point when the deployment was going on. So for now, we have temporarily just said that, okay, let's just use DHCP v6 with RAs for gateways to be known and just disable the advertised autonomous flag in RADVD, which is of course not the recommendation, but it is what we have done temporarily to see that our deployment progresses for now, and then we can take care of it. The next observation is in terms of routing. So we have static IPv6 routes that we have configured on core switch, and one thing that we identified is, so actually our core switch is a bit old and it's about to be end of life. So we are in the process of replacing it, but when we started the deployment a couple of years ago, we would see that if and when any of our L3 managed core switch went down in our data center and rebooted, the static routes just wouldn't work. And we had to manually remove the routes from the table and had to enter them again, and that would solve the problem. So we started looking into why this is happening, although these core switch didn't reboot quite often, but then whenever it did, some manual intervention was needed. So we wanted to understand what can be done. So the suspected cause is that the neighbor solicitation is not being sent by the switch to the router. And unfortunately, we are not able to replicate this behavior on that core switch because it's an old firmware. Patches have not been put up on that, and we don't want to touch it until the new thing comes up, because if we touch and something happens, the whole network will be down for the entire campus. Also, we found out that the re-establishment of the routes with IPv6 was taking a lot longer. It was taking about 2.5 minutes of time for the IPv6 routes to get re-established in case the core switch went down. And again, we were a bit surprised because IPv4 would just come up almost instantly. And since we are using dual stack, we didn't face too much of downtime because IPv4 would start working immediately for the clients and IPv6 would take its own time to come up. But again, it's not clear for us whether this is a bug or it is an expected outcome. But we believe that we will, write some eBPF scripts and use BPF trace that will help us in understanding this behavior as to why we are facing this much amount of time for the IPv6 routes to get established. There are some other observations depending on the firmware that we use, depending on the vendors that we have. As I mentioned, our firewall did not actually support IPv6 for web filtering. We also saw that support for monitoring BGP v6 was not available. Our BGP router actually runs on Viata operating system, and Viata did not support the MIB for BGP 4 version 2. Primarily at that time, FRR did not support it, but I saw recently now the support has been added, so maybe they will update it. But temporary workaround for us was to use the bgp.tools, which showed us the status of our BGP routes for both v4 and v6. And we also found in some of the switches that we had in the testbed that IPv6 and MAC binding just wouldn't happen. It was not possible for us to have the MAC binding done. But anyways, those switches are not the one that we have in production, so we didn't worry much about it. But we did observe this in our testbed at that time. Also, we saw there was lack of support for some debugging tools like HPing. They don't support IPv6 for debugging. And yes, this is a very well-known problem, lack of support for DHCP v6 in Android. So we actually had to run a separate router in our campus to do RDNS so that our actually Android users can still work. But yes, we found this to be quite a bit of a problem. And surprisingly, when we migrated our campus to EduRoam, we also noticed that the federations that are proxying EduRoam to our campus, those proxies don't support IPv6 yet. So that was another observation that we had there. These are some of the statistics from our campus deployment. This is only this is a stats only for the traffic that goes towards Cloudflare, and then we have this is a status of our V4 and V6. For some reason, I'm not sure why APNIC measurements are not showing the things. I'm yet to understand what this is happening. We collected these traces at the end of the month of February. I still haven't gotten a chance to see why the measurements of APNIC don't show adoption that way. We also have some local measurements done where we are tracking V6 and V4 users. And we have some measurements from RIPE and APNIC. We have also deployed RPKI and ROV. And here the APNIC shows clearly that we have 100% support for ROV. And these are some of the stats that we got from BGP tools. This is our thing. We have a separate ASN and we have 2 upstreams. And this is a track that we have. That's it from my side. Thank you so much. This project was funded by ISF Asia. And that's a small campus of NITK. And we have an VNC and we have a sea beach view from our campus. So you're welcome to visit India at any point of time. Thank you.
You have some questions, so Jen.
Jen Linkova. First of all, a question, I have not checked the agenda. Are you presenting this at V6 Ops by any chance?
No, not this time. But I'm happy to. If there is some room, I can do that.
I guess you might want to talk to the chairs.
Sure.
Could you go to slide 5, please?
Yes.
Yes. So you later mentioned that you had to deploy a separate network for devices which do not support DHCP-only address assignment, right? So I'm trying to understand, why do you have an issues with tracking devices if you have .1x enabled? So you obviously know which MAC address shows.
So we do not have .1x for the wired devices yet. We have only for the Wi-Fi devices. So I can go back to this one. So we have 802.1x authentication only for the Wi-Fi users.
Okay, and your problem with temporary, and you do not have control over devices on the wired network, I assume?
Yes. And this experiment, as I mentioned, was done during our testbed setup. So our testbed was mostly wired testbed. We didn't have wireless devices in the test.
So you have like wired Android devices?
Sorry?
Wired Android devices, because you said you have...
No, not wired Android devices in this one. The Android devices were at the last when we enabled the IPv6 in all our hostels for 7,000 rooms is when we found the problem with Android. But that was not on the testbed. The Android one was the live deployment. These observations were mainly on the testbed. And even otherwise, we have about 25,000 devices. Quite a few, more than about 8,000 devices are still wired, and they don't have 802.1x authentication.
Yes, so just be careful, because if you eventually would like to move to V6 only, you might need to still have Slack for CLAT.
Yes.
So your deployment might cause some issues. And secondly, if you do want to know which device sent what traffic, right, it might make sense to look at neighbor discovery cache on the routers, and you can take a look at RFC we published about address registrations when devices report addresses they assigned via Slack. Okay. So you can know which devices were generated, which addresses.
Yes, thank you. Thank you for that input.
Tobias Fiebig, Max Planck Institute for Informatics, and I wanted to know whether you had a legacy IP address allocation before doing this transition.
I'm sorry, I could not get the question.
Did you have a legacy IP allocation before doing this transition?
Legacy?
Before.
I'm not sure I understand the question. So
IPv4 addresses. Did the university have IPv4 addresses as an allocation before doing this?
Oh, no, we had it from the ISP. We didn't have our own allocation.
Okay, thank you.
Yeah, but for IPv6, we actually got our own allocation. Yeah, we got it from NIXI, which is the National Internet Exchange of India. But there's another thing that NIXI does. If you take a /32 IPv6 block, they give you IPv4 for free. So I expect this reaction, that how is it possible that somebody gives you IPv4 for free? But then since, the /32 IPv6 is a big chunk, they give you IPv4 for free and then they give you an ASN. So now we do have, since I got a /32 IPv6 and I pay for it, and they give an IPv4 for free, I wouldn't say no. So I said, give me that allocation. So I do have now an allocation, but not before we started the deployment.
So just to clarify, and I'm not 100% sure how it works in APNIC with India, but you do not have like a direct thing from APNIC, but instead from an NIR, or
yes, it's a local RIR.
No, is it an LIR or an NIR?
Okay, so we just call it as Indian registry.
Okay,
and
Indian
it takes it from APNIC, and then we get it from here.
But
we do have an option to either directly take it from APNIC or we do have that option, but we chose it to go and take it directly from the Indian registry.
Looks like the queue is empty. Oh, okay. We have an unregistered queue participant.
Okay. So, Tomek Mrugowski, ISC. So, which DHCP server did you use?
Sorry?
Which DHCP server did you use?
Oh, we used the Kia DHCP server.
Okay. Good.
Thank you.
Think we're good. Thank you, Mohit.
Thank you, everyone.
One more presentation. On Civ. Under all yours. Clickers there should work.
Hi, this is Andre ISC. This is not so much like operational presentation, but software engineering presentation. But it's so much fun that I had to present to you. Do you know the LRU algorithm? I just like a quick overview. So this is least recent used queue. So if you have a queue of requests and you have a full cache somewhere, then you just start evicting from the end and adding at the head and go on and go on. So if there's a cache hit like this, the D is already there, then you move the D to the head of the list, and you end up with something like this. So this is just basic LRU, how it works. So the Sieve algorithm isn't my work. I just found it really cool research how to improve the LRU algorithm. I implemented it in Bind. I'll show you in the end. So this is how the new improved Sieve algorithm works. So instead of like moving, this is not the last stack. Yes. Sorry. I'm missing some pictures in there. Really? Yeah. Can you show the page on the screen? Something wrong happened. Or I can bring my own laptop if that helps. Does it help? No. So trying to find a Sieve. Sieve LRU or yeah, the one. Yeah. And there's a video in here. Up here as well. So I'll show you the video from the web page to fix this. Sorry for that. Somewhere an email got lost. Okay, so this is the video from the authors of the algorithm. So basically, the algorithm adds a pointer called sieve hand, and instead of like moving on a cache hit, moving the item to the head of the list, it just marks it as visited. So this will happen in a moment, and you evict whatever was not visited under the hand if you need more space. So if you find something that has been marked, you just unmark it and move. And if it's not marked, then you just evict it and move the item to the head of the item. This is one big. Can we go back to the slides? This is one big advantage, because for the cache hit you don't have to lock the list. So you just mark the item, and that helps a lot with a contention among the threads. Now the implementation, I hope it's in those slides, I think so. So this is how the end of the cache looks like after each algorithm finish. On the example, I'll then upload the new slides. We will upload them to the IETF. So, so the difference is, if you have a cache hit for RU, it moves the object to the head, it locks the list. For sieve, it just marks the object, no list level locking. For cache miss, you need to block the list, and you, in both examples, you add the item to the head of the list. For RU, you evict the item from the tail. For sieve algorithm, if it's marked, unmark, and move. And if it's unmarked, then evict. The concepts are lazy promotion and quick demotion. So for lazy promotion, only promote the cache objects at the eviction time. So you don't do the work for the cache hits. For the quick demotion, again, the concept is that you remove most objects quickly after insertion. That helps. So the beauty of this algorithm is that it's very simple to implement. So if you look how the starts from when I implemented in bind, it removed 441 lines and it just added 144 lines. So it's like 4 times less lines, because I removed both TTL-based cleaning and the RU-based cleaning and just add this new algorithm. And for small caches, this is the reverse logarithmic graph. So if you haven't seen this before, you basically want like this, want the line to be in this the left bottom corner, because it means how many queries were responded under here is 1 second, and so this is slowest percentile. So it means that something like, for the blue line, something like 99.5 were not responded at all under 2 seconds. But so bottom left corner is better, basically. So this is the cold cache. For the cold cache, this is the second part of the test. It's even gets even better. And this is a very small cache, just 128 megabytes of the cache for the DNS. It helps a lot. It also helps a lot with this is the memory in time. So the memory gets more stable and it's less, fuzzy. And for the CPU, you can also see that the CPU usage is much more stable with the new algorithm for the small caches. For the large cache, like 30 gigs, so we don't hit the limit at all. It helps a little bit as well, because there's less contention during like cache hits. Again, this is the cold cache, this is the hot cache. This might be just a measurement difference. And for memory, it helps a little bit with the memory and a little bit with the CPU, but just a little bit. Again, it can be just a measurement artifact. But with the small caches, the difference is huge. So I have it like for the development version and a simple implementation. The questions are we going to keep the TTL-based cleaning? Probably not, because there's no difference. And I have some more questions to answer. How does this behave with the large caches? So if I fill 30 gigabytes of data, how will it behave? How will it behave with the pseudo-random subdomain attack and stuff like this? So before we just plug this in out of excitement, we should, answer these questions. And that's it. I hope this was as exciting as it was for me to find this algorithm.
Questions for Andre? Seems like the queue is empty.
Okay.
Thank you very much. I'm told it's informal. Is there anything anyone else wants to say? Hopefully I won't get kicked out of doing this by asking such a question. We have about 20 minutes left. Okay, well, thank you very much for coming to IEPG, for allowing me to host, and enjoy the rest of the IETF.